Alright, so the very last thing you did at the end of grade 9 when it came to lines was looking at what was called a linear system. Now, if you don't remember what a linear system is, that's okay. It really is just looking at a set of two or more lines. Now, 99% of the time it's going to be just two lines, but it is possible to have more of them, more than two. But really, if you're looking to solve a linear system, all it means is you're looking to find the point of intersection, or POI, of all the lines involved in the system. And that's what you would have done back in grade 9. You'd be given a couple of equations, or maybe a couple of situations if you're looking at some real life examples. You would plot them both on a graph, find where they intersected, and then make determinations based on that. And again, what we're looking for is that point of intersection. Okay, now there's multiple ways to find that point of intersection. The way you would have looked at last year is to do it by graphing. Okay, there are ways that are a bit more algebraic. We're going to be looking at those later on this unit. So a typical type of question you would have looked at back in grade 9 is one like the following. So we have a video game rental store or service online that rents video games for $3 each. This one's called Games to Go, and you don't have any membership fee up front. Okay, there's another store called Video Gamers that they rent games for a little bit less, $2, but they charge $10 membership fee up front. Okay, and the question is, which rental place should you use? This would be a typical type of question you would have seen back in grade 9. Okay, and what you would need to do first is create equations for each of these stores. So what I'd like you to do now, very quickly, create an equation for Games to Go, and create another equation for Video Gamers. It even tells you what variables to use. Let x represent the number of games rented, and y be the cost in dollars. So take a minute to do that and push play and ready to see the answers. Okay, so for Games to Go, because there's no membership fee up front, you only pay $3 per game, the total cost is going to be 3x, so 3 times the number of games you rent. For Video Gamers, it's only $2 per game, so 2x, but you pay $10 up front, so 2x plus 10. Okay, so if you want to try and determine which rental place we should use, we have to look where, we're looking for the point where both of these stores are going to cost the same. We're going to have to put both of these on a graph. Okay, so try and graph these on your own. Again, it makes a good review from grade 9. Put them on a grid and see if you can find the point of intersection, and we'll discuss it when you're ready. So push play when you're ready to do that. Okay, so let's take a look at the graphs here. So I did it in Desmos here. Now, Games to Go, if you look at the equation, it has a slope of 3 and a y-intercept of 0. So if I start at 0 and I count up 3 over 1, I get another point. Up 3 over 1, get another point, and so on and so forth. I can continue my line off that way. For Video Gamers, the one in blue here, it's y equals 2x plus 10. So I start at 10 for the y-intercept, and with a slope of 2, I go up 2 over 1, and continue getting points in that respect. So up 2 over 1, up 2 over 1. And again, what we're looking for is a point of intersection. Now, you can see it very clearly on my graph, and it should be on yours too if you drew a nice graph. You should be able to see the point of intersection being at 1030. Okay, and remember looking at the variables here where x was the number of games rented and y was the cost. This is saying that at both of these stores it costs $30 to rent 10 games. So the question is, well, based on this information now, how do we decide which store to use? Well, you can see the cost is going to be lower in the red line, Games to Go, as long as you're renting less than 10 games a month. The moment you go beyond 10 games a month, you'll see that the blue line is lower, so video games will be cheaper. And again, this is a typical type of question you would have done last year in grade 9. But really, what we've done is you solved a linear system. So the solution to this linear system is going to be the point of intersection at 1030. And then we can use that to answer the question, which rental place should you use? Okay, but in general, if you're looking to solve a linear system, we want to do it by graphing. You're going to graph each line you have, look for that point of intersection, and you'll have your answer. Okay, so here's what I'd like you guys to try and solve by graphing. So I got two equations here, y equals 2x plus 9, y equals negative 2 over 3x minus 7. Try and graph each one, and I'd like you to try and find the point of intersection of these two lines on your own. Okay, you can push play and ready to see the answer. Okay, so here's what the graphs look like over here. So y equals 2x plus 9 has a y-intercept of 9 and a slope of 2, so you go up 2 and over 1 to the right to find new points. The second line, which is in purple here on the graph, is y equals negative 2 over 3x minus 7. So the line has a y-intercept of minus 7 and a slope of negative 2/3, so you go down 2 and over 3 to the right again to find new points on the line. So if you look for the point of intersection, you'll see it occurs right here. Okay, so the solution to this point of intersection is just going to be that point. So that POI is at -6 for the x and -3 for the y. Okay, so you can write your solution as a point like this, or you can say the solution is x equals -6, y equals -3. Okay, so two possible ways of writing the answer. You can write it as a point, but remember that the point just refers to x and y coordinates, so you can write them out that way as well. Okay, so again, as long as we have the graph accurate and correct and clear, it should be pretty. As long as you have a nice answer, it should be very clear to see that point of intersection. You just read it off the graph. Now, one thing you should get in the habit of doing once you finish solving a linear system is doing a formal check. Now, you may have done some of this back in grade 9, but if not, that's okay. I'll show you how. Now, remember, in order to do a check here, this is only a solution if this point is on both lines, both the red one and the purple one. So we can see it's there on the graph, but how do we know we didn't make a mistake on the graph? So we can check by algebraically using this point in the equations. And if this point happens to make both this equation and this equation work, i.e. left side of the equation equal to the right side of the equation, then you know that the equation works. So let's actually do that here. We'll do a check. And again, to do a formal check, you take the left side and right side of the equation and look at them separately. So I'm going to start with equation number 1, which is y equals 2x plus 9. Okay, again, separate into two sides. So left side is just y, so left side of the equal sign, and the right side is 2x plus 9. And again, what we're doing here is we're taking our solution, the x equals -6, y equals -3, and putting it into both left side and right side to see if the two sides agree with each other. So if I do that, I'm going to have y equals -3, okay, because that's the y for my solution. And if x is -6, it's going to be 2 times -6 plus 9. Okay, so if I simplify here, 2 times -6 is -12, plus 9 is -3. So you'll see that this happens to work, that both left side and right side are the same. Okay, now this isn't enough to prove that our solution is correct, because it only works now in this equation. We have to prove it works in the other equation as well. So I'm going to let you guys try that on your own, just to make sure you can go through the process. So I want you to take the equation y equals -2 over 3x minus 7, split it up into left side and right side, sub in the point, and just make sure you can get it to work out. Okay, it shouldn't take you too long, and push play when you're ready to go through, when you're ready to see the steps done in front of you. Okay, so there's a check for the second equation. You can see the process is identical. Maybe this one's a little bit trickier because there's a fraction involved. They have to multiply through. But you'll see the right side simplifies the same thing as the left side. And again, if I ever ask for a formal check, this is what I would expect you to do, to check your answer into both equations. But it's also something you should get in the habit of doing on a test once you're finished, making sure your answers are correct, because it's a good feeling to know that your answer is correct before you hand in the test. And if you make a mistake, if you realize you made a mistake somewhere, it's better to find out right away rather than after you get the mark back. Okay, so it's a good thing to get in the habit too once you have time to do it. Okay, so let's take a look at another one here. So I'd like you to solve this system graphically as well. So again, same thing, two equations, try and graph them both on the same grid and see if you can find the point of intersection. You notice I made this a little bit trickier here. I gave you, none of them were in slope-intercept form like the ones in the last problem are. So with the first one, remember this is point-slope form. So if you remember what point-slope form tells you, this will tell me that we have a slope of 1 over 3. And this equation is not giving me the y-intercept, but it does give me a point. So going backwards from the equation, this would give me a point at x equals 2, y equals 1. So if I'm going to make my graph, instead of starting at the y-intercept, I'm going to start at the point 2, 1, and use my slope from there. Okay, the second equation is 3x minus 2y equals 12. You have to either put that in slope-intercept form or solve for the x and y-intercepts and make the graph that way. So give that a try on your own. If you're stuck, ask for help or work with a partner, and see if you can find the point of intersection for this one. Push play and go through the answers together. Okay, so before we get into a discussion about the actual POI, let's double check our graphs here. So again, for the first one, I'm given a slope of 1/3, and that passes through the point 2, 1. So starting at the point 2, 1, I go up 1 over 3 to the right, up 1 over 3 to the right, and so on and so forth to continue making my graph. Okay, so that gives me the first line there. That's the one in purple. For the second one, I could have found the x and y intercepts, but I chose instead to put it into slope-intercept form. That's a form we're a bit more familiar with. So I rearranged the equation, subtracted 3x from both sides, and then divided both sides of the equation by -2. So I get y equals 3 over 2x minus 6. So starting from the y-intercept to -6, I go up 3 over 2, up 3 over 2 to the right, and so on and so forth. Now, the one problem that you might see here is you see the point of intersection is around here. This is not a nice point to read on the graph. Okay, and you might just think, oh, maybe it's the grid that I'm using that's not very, very clear. Well, let's take a look at a better graph on Desmos and see what the actual point of intersection is. Okay, so here we're on Desmos with the exact same two equations here, and you can see the point of intersection here when I click on it here is messy. Desmos approximates it as 5.429 for the x and 2.143 for the y. Okay, now this is obviously an approximation as well. This is not something you could reasonably be expected to get just by looking at a graph. You could look at the graph that you created and maybe approximate this as being about 5.2, 5.3 for the x and maybe 2.1 or 2.2 for along the y, but you can't get the most accurate answer out there. Okay, so there has to be a better way because graphing does not always give you a perfectly accurate answer. And there is a better way. It's called using substitution or elimination, and we're going to be looking at that over the course of the unit. But just keep that in mind that while graphing, since it uses everything from grade 9, isn't too bad to use, it's nice and familiar, it kind of falls apart if the point of intersection is not a nice whole integer value. And in real life, whole integer values do not happen very, very often. Okay, so it's something to be mindful of. And keep in mind as we go through the unit that eventually you need to transition to doing the algebraic way of solving as well. Okay, so with that in mind, just one more example. And this one I'm just giving you two equations, and you'll notice here I'm not asking you for the solution. I'm asking you if the ordered pair or the point, okay, if you don't know what an ordered pair is, really just another name for point, is 1,4 a solution for this system of equations. Okay, so remember, if it's a solution to the system of equations, the point of intersection, so it's on both lines. So there's a couple ways of going about finding this one. Some ways are shorter than others. I would like you to take a minute or two on your own or with a partner or small group. Try and figure out this one together. Maybe you can come up with a couple different ways of solving this. And again, just see if 1,4 is a solution to this system. Okay? When you're finished, push play and we'll go through the answers together. Okay, so one method you guys may have come up with is to just actually try graphing these lines, find the point of intersection, and seeing if the solution has to be 1,4. Now I'll tell you right away, this is not the faster solution. Let's take a look at the graph and see if we can get an answer from it that way, okay? So I'm going to graph x plus y equals 5. Okay, I would actually rearrange this into slope-intercept form as y equals -x plus 5, slope of -1, y-intercept of 5. And I'll do the same thing over here, 7x is equal to 2y, which means y equals 7 over 2x. So slope of 7 over 2, y-intercept of 0. So let's quickly make a graph here. And is 4,1 a solution? Looks like it's pretty close, but what's going to happen if we zoom in here? So I'm going to zoom in here on the graph. Okay, and you can see that the point 1,4 is actually over there. It's not the actual solution. The point of intersection occurs a little bit away from that. So from that picture, we can sort of see, hey, this point 1,4 is not a solution to the system. But that takes a while. We had to graph each one. So the faster way, which I'm going to strongly recommend that we do, remember a couple slides ago when I showed you to do a check? Well, that check is to see if the point is a solution. And remember, if it's a solution, it's a point that's on both lines, so it would have to make both equations true if you subbed it in for x and y. So what I'm going to have you guys do now is attempt to check. Do a left side, right side check for each equation with the point 1,4 and see if it works or not. Now, you can already tell by looking at this graph that's not going to work, but I need you to go through the check process on your own and see that it doesn't work when the point is not a solution. Okay, so I'd like you to do a check and push play and you're ready to go through the answer and just check that you've got it right. Okay, so quickly run through what's happening here. I took the first equation, x plus y equals 5, sub the point in 1 and 4 for x and y, and I'll see that for the first equation it works. I get both sides equaling to 5. However, it needs to work in both equations. When I sub it into the other equation, I get one side being equal to -1, the other side being 0. And that's enough to show that this point is not a solution. Okay? So that's it.